Recording is rolling. It is Monday, September 30. So I'm going to take the first few minutes of class to debrief this modified Atwood half the lab that you guys did back on Friday. Right. Most of the class day, you guys are going to be doing this classic Atwood. I'll show you guys a little bit how to set that up, but in a few minutes here. Right. Then you guys remember on the opposite side of this page, of course, was the friction lab. Can you guys turn this page into the grade tray by the end of class? You see that? Right. And then yeah, there'll be 2 lab grades, friction lab and Atwood lab right there. My plan the rest of the week, I want to take some days to do some puzzles, some days to do some other labs with you guys, probably a pre-response question. I'm working on getting your guys' quiz together, closely together. Got to finish some things there. Guys, here's what I'm thinking for chapter 4 puzzles. Let's have a due date as 1 week from now, Monday, which I think it should be plenty of time by now, right? You should have finished some of it already. I'll show you guys how to solve these Atwoods, and then give you guys some time later this week to solve some puzzles. So I think Monday's a plenty good due date for that. All right, you guys good? What we're doing so far? All right, so let's look at this modified Atwood class that you guys did back on Friday. Guys, oh, sorry, one more thing. We got a school play coming up. This is looks like October 3 through 5, so a few days. So school play. Ooh, that's exciting. All right, so you guys were doing this modified Atwood half the lab. All right, so let me show you guys how to solve this going through dynamics, because the way you did back on Friday was you went through kinematics, which say you replace different masses, right? You got an M1 and M2, or try different versions, but you really kinematic motion and started from rest, moved so far and so much time on a stopwatch, you're able to calculate the acceleration. And then the puzzle, could you connect that back to the masses? So you could have what was the acceleration as a function of the masses. That was kind of your goal, right? I'm going to show you how to do that, like through Newton's second law of motion, and furthermore, how to get the tension in the string, which I didn't even ask you, but I'll show you guys how to do that too. So we're going to do all that right here. All right, so you guys remember Newton's second law of motion? I got a poster for that I updated. Oh, well, here, actually, I got it kind of right here. Right, you guys remember this is Newton's second law of motion right here? Oh, look at that. I updated this over the weekend. I threw a little script net on that. You see that? I should have always had that. So there you go. There's Newton's second law. So a net force driving a mass is going to cause it to accelerate. All right. Well, let's figure out what's the forces, what's the masses going on here. Oh, no, I see possibly 5 or 6 different forces going on. You guys see the weight of M1, that's M1G. I see that. I see this tension, this tension. Hey guys, do you guys think that one string could probably only have one tension in it? You guys think? Yeah. All right. No, maybe it could possibly get a little trickier if this pulley has significant rotational inertia and friction on it. We're not worried about that, right? But that aside, yeah, I think this one string should have one tension. I think this is the same tension. Okay. Right, so we got that. I see M2 has its own weight, but also a normal force from the table surface. Guys, if this is a flat table, horizontal table, is this M2G and this normal force canceling out? Right? What if I cut the string? Would this, if this block started at rest, would it even move at all? No, because there would be no external force. Well, there'd be, I guess, 2 forces, but they cancel out. There's no net external force. No net external force. Okay? Which reminds me of another poster I also updated. Look, I threw in the word net for first law of motion. Net. You need an external net force. Yeah.
If the part moves backward a little bit, because there's tension on the string, and on the string is kind of slingshot backwards a little bit.
Maybe if there was a force that didn't go away right away, right? Yeah, if there was like a spring holding it in place, yeah, that would be true. If you cut the string, it would fly back, right? But if there's just a friction force and nothing else, if you cut the string, then that friction force will immediately dissipate, so it just goes away with it. And for you guys, you probably said friction force was negligible because it's on Hot Wheels. Anyway, so that's why I put it in light gray, so it'd be really easy to ignore. Right? So pretty much that was the whole thing right there. I think it's what you guys happened. All right, so here's what we got. We got these 2 blue forces are canceling out, so let's throw those out. This tension force is just internal to the system. It's not an external force to the 2-block system. So maybe it's just holding everything together. Kind of like maybe if I wave this pen around. What's driving the pen? Well, it's an external force from my hand. But hey, do you think there's a bunch of little plastic molecules that are just holding the pen together? But that's just keeping the object together. That's kind of like this tension force right here. So really, there's only one force that can hone in on that's really driving the system to move. Isn't that just the weight of M1? Right? That's driving the whole system. That effectively is the net force from a system point of view. And so let's do some math here, right? So I'm going to do method 1. I'll show you guys 2 methods to solve this. Method 1 is what I've seen AP call a whole, oh, you guys are probably writing this in your notes, right? Whole systems approach. Whole systems approach, right? So this is a, here, modified Atwood. All right, all right, so I'm going to go Newton's second law of motion, acceleration of, I'm going to look at the whole system because, see, I know that the M1 is accelerating down and M2 is accelerating to the right, but wouldn't they have to have the same acceleration because they're tied together with the same string, they move the same distance at the same time, the whole deal, right? So system as a whole is what is the net force divided by the total mass, right? There's Newton's second law of motion. Newton's second law, right? Okay, right? Right. So for the whole system, right? Again, one block's moving aside, one's going down, whatever. Right. Guys, what did I say was the net force for this situation? M1G, right? So the hanging weight, M1G, is driving the whole system to move. Right? And guys, how much total mass is being moved around? Is it M1 and M2 together? Should I say M1 plus M2 like that? Right, guys think? Right? I think that right there is going to get it. Right? The hanging weight divided by the total mass. Right? Okay, let's get that. Right. Which, by the way, is what I got these boxes over here. Here's Newton's second law of motion at the top. Here's, hey, look at this yellow box right here. Isn't that exactly what I just wrote? That is that. You see, it's a match. Right? If you throw in that friction force, you'd have to subtract that off from the numerator. But if that didn't exist, then it would be exactly that, wouldn't it? Ah, yes, that too. Right. All right. Oh, now once you got that, you can solve for the tension in the string if you want. Here, let me do this way. I'm going to solve this with numbers. That's in terms of variables. Let's throw some numbers on the board. Let's say, for example, if M1 equals, I'll call it 1 kilogram, and M2 is 4 kilograms. Okay, just make something up. All right, let's try this out. Okay. So the acceleration of the system in that case would be, let's see what it would be. So you got M1G. Guys, how many newtons of weight would that be? Yeah, 9.8 or 10 newtons, about somewhere in there. Right? So 1 kilogram at, I'm going to round this a little bit to 10 meters per second squared just for the notes here. Okay? And then that'd be 1 kg plus 4 kg. Right? Well, that's 1/5 times 10. Acceleration of the system could be maybe 2 meters per second squared, right? For just for those particular numbers, right? And I think that aligns too with I think if I remember right, I was having you guys back on Friday think about boundary conditions, which is maybe sometimes a good way to start thinking about a puzzle. Is what if M1 was extremely small? I bet the acceleration would be extremely small. What if M1 was extremely big compared to M2? I bet the acceleration would approach 10 meters per second squared to a free fall, like that. Right now, okay, this kind of aligns with that, right? Like on a spectrum from 0 to 10. Ah, that makes sense, right? Right. How about the tension in the string? Now, the tension in the string, you want to focus on one block or the other block, and it doesn't matter, and they'll both give you the same thing. Right. So continue tension in the string. Right. So let's say I pick this one right here, right? The hanging block. Here, I'll split my paper and do it both ways. Right. So we got the hanging block. Here, I'll just call it point of view M1. Right, and then later on we'll do point of view M2. Okay, how about that? Right. Right, so from the point of view of M1, it's got this is kind of like elevator physics, isn't it? It's like an elevator. I got M1G pulling down, got some mystery tension force pulling up that we want to solve for. Right, so F net equals MA. F net is I got M1G pulling down, I got mystery tension force pulling up. That's going to result in mass times acceleration, isn't it? Okay. Now, I think we know all these other numbers. So if I plug in my example numbers, I'd have like 1 kilogram here, 10 meters per second squared, minus the mystery tension equals, oops, M1. Right, so this is 1 kilogram, again, times. Now, here's where I'm going to pick up from before. You guys remember I was getting 2 meters per second squared for those particular numbers? right? So go ahead and do this right here, doing 2 meters per second squared. Boom, boom. Okay. So I got 10 newtons here, got 2 newtons here. Subtract that, add this, right? So 10 newtons minus those 2 newtons equals, and then add that over the tension force. Okay. I think the tension force has to equal 8 newtons for this to play out exactly like that. Right. How about from the perspective, the point of view of M2? Right. Now this might have a bunch of forces on it, but really the tension force would be the net force just on that single block. Right. Let's see if this gives us the same. It should be the same answer. Let's see if it is. I'll do F net equals mass times acceleration. In this case, the net force is the tension force. Right. That's it. Right. All the other ones just cancel out or negligible. And that's what did I say M2 was 4 kilograms. We're doing 4 kilograms, for example. Let's do 4 kilograms, 4 kg. Oh, and this block's going to be accelerating at, we were saying 2 meters per second squared is what it has to be. Okay? So it has to be going 2 meters per second squared. So the tension force equal, oh, and look at that. It's 8, and then kilogram meter per second squared is newtons. It's 8 newtons just like before. Bing. So from both points of view, of course, they give the same answer. So if this was a AP question, of course, you got a time limit. So maybe you just pick one block, but it doesn't matter which block you pick. Right? Right, guys get that? Right, guys good? All right. Now that was all method 1. But this is usually how I solve these with students in class, called a whole systems approach. So I'm looking at the system as a whole, like a macroscopic point of view, and then I narrow in. Okay? So I'll say start with Newton's second law of motion, and then I'll jump to this yellow box, which is kind of like the answer to the lab. Okay? And then if I want to get more details, say, hey, I wonder what the tension of the string was. That's where I did, say, these green boxes down here, and I solved the tension of the string. Okay? But you could do this from the other perspective. You could go the method 2. Method 2, I'll call it a system of equations. System of equations. Right, and a lot of textbooks, a lot of instructors will actually teach it this way. Okay. Oh, yeah. For the hanging one, that's true. Right, this weight down minus the tension is the net force. Yeah. Yeah. Okay. Yeah. Okay. So just go back a little bit. Yeah. M1G minus the tension force is the net force on the hanging one, and only the tension force was the net force on the M2 up here. Okay. All right. So what if I do a system of equations? Now, a system of equations actually starts with these 2 green boxes. Of course, you should end up getting the same answer regardless of how you approach this. This is more like a micro as opposed to a macro perspective. So I can say M1G minus tension force is equal to M1A. That's one equation. And the other equation is the other block is just the tension forces driving M2A. Right? So here's my system right here. Right? Which, yeah, that's exactly what I got in these 2 green boxes. You guys see these 2 green boxes? That just is my system. Right? It's Newton's second law of motion from the perspective of M1 and M2. Okay? Right, now let's do some example numbers. So I was saying M1 could be 1 kilogram. So 1 kilogram, 10 meter per second squared minus, right? Now, if I'm starting this from scratch, then I don't know what the tension force is yet, but I also don't know what the acceleration is yet. So I'm making believe I'm going back and starting this from scratch. Okay? Okay. And then from the perspective of the other block, I got mystery tension force, again, we have to solve for, is equal to, now M2 I've been calling 4 kilograms. That's been my example number, so I'll do that, times the mystery acceleration. Again, we got to solve for. Okay, so there's the system again, just with the example numbers plugged in. Okay. Right. All right. Now what? Now I could do. There's different methods you could use to solve system equations. Can you guys use substitution? Substitution. Right. You guys see that? Right. Now if we do substitution, ooh, look at this. I got tension force is equal to 4 kilograms times acceleration. Can I just substitute that right up in there? Right, and then bring this down. Let's try that. So 1 kilogram, 10 meters per second squared, that's 10 newtons right there, minus, and then instead of tension force, I'll do brackets to show you guys that I do a substitution here. That's just 4 kilograms, 4 kg, times whatever the acceleration is. Right, and that's going to result in 1 kilogram times also the same acceleration. Again, it has to be the same acceleration because blocks are tied together. They both the same type motion. One's side, one's down. Same magnitude though. Okay. All right. So I got 4a here. I got 1a here. Can I just add the 4a over and get 5a? Can I do that? Okay. So 10 newtons is equal to 5a, well, 5 kilograms times acceleration. Divide both sides by 5 kilograms. Hey, newtons divided by kilograms. Newtons per kilogram. Is that the same thing as meters per second squared? Yep, it's the same thing. Newtons divided by kilograms. That's Newton is kilogram meter per second squared divided by kilograms. Good. And then the number is 10 over 5 is 2. Okay. Units, meters per second squared. Don't forget your units, 2 meters per second. Hey, that's the same thing we got before. Right? Remember, back earlier in class, from a whole systems perspective, I was also getting accelerations 2 meters per second squared. You get the same thing. Right? Right. Now, once you got this, you can take this and plug this back into these equations. But that's basically what we did just right here to get the tension. And you could, again, pick either block. Okay? So this 2 meters per second squared times this 4 kilograms gives you 8 newtons tension, which is the same thing we got before. So it's the same thing. There's two perspectives. You do a whole systems point of view, macro, or you can do system equations like a micro point of view. Right? You guys got that? Right. Pretty good. Pretty good. All right. So next thing, let's move on to second half of the lab, which is the classic Atwood right here. There we go. Right. Okay, so this is a little bit different setup. It's gonna have a little bit different solution. But I bet you guys can figure this out. Give you guys some pointers before you guys head back there. Now this one here. One thing is how to fit the string in the groove. I mean, there's a bunch of little technical things I can help you guys out with. And so let me show some common ones here. Here, can you guys do this? Can you guys push the string through the side like this? You guys do this? Notice I just pushed it through the side like that. You guys see that? And then once it's pushed through, I can just hook the string right into this groove just like that. Okay. Now, guys, don't push it through both sides. Well, I guess you could, but it's a little harder. Here, if you just push it through once, can you just hold this black bar vertical? And it's just really easy. Just zip, 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 zip. Could look just like this, couldn't it? Okay. Probably want a string. I'm going to advise about 1 meter long at least. Okay. Use probably 1 meter long string. All right. And then, do you guys see I like tied a loop on the end? You guys see I tied a loop right with the knot? Here. I always forget every year, but a lot of students don't know how to tie a knot. So here, I'll show you guys real fast. Is just like start like tying your shoes. Right. Boom. Go like that. Right. And then just do that one more time. And then pull that, and you probably got a pretty good knot. If it happens to be a slip knot, you can just do it a couple more times, it usually stays. Right? But if you have a loop, the advantage of a loop like that is it's really easy to just hook on new masses. Okay? So you can just swap them out real fast as you need to, something like that. Okay? All right. How about this? Let's think about some boundary conditions for this classic Atwood. Okay. Guys, what if these masses are the same? Like here, I got 200 grams right here. And I have another 200 grams right here. I'll just hook onto the other end. It's already a loop here. Guys, 200 and 200. If I hold this up, what's it going to do? Yeah, it's already should be equilibrium. See if I, of course, hold the pulley in place. Right? Yeah, that's not moving at all. You guys see it not moving at all? Right? What if I did the other extreme? What if M1 was equal to 0 and M2 has all the mass? How much is going to accelerate? Yeah, at the full rate of gravity, full 10 meters per second squared. Okay. What if I have my 200, 200, like I do right here, and I find an extra little 20 grams? So I got, say, 220 versus 200. Okay. Now what do you think is going to happen? Now I'm breaking it right now, but when I let it go, is it going to move? Is it going to accelerate? Yeah, because there's going to be a net force. Here we go. You guys think you could time how much time it takes for those masses to swap positions like that? Right? What do you think is easier to time, if it accelerates quickly or slowly? Yeah, if it accelerates slowly, that's probably a little easier to work with. All right, so I'm going to hang up the recording right there. You guys get your data, figure out the answer, and pop that lab page in the grade tray by the end of class.